Hi, my name is Guangfeng Yu. Today I will present the research plan to investigate MANIC's ability to produce deep nulls for direct exoplanets imaging. Monolithic Achromatic Nulling Interferometer Coronagraph, or MANIC, is a nulling interferometric coronagraph designed to detect and image exoplanets directly. Exoplanets are distant planets that are beyond our solar system. Upon direct viewing, exoplanets are small and dim compared to their host stars, making them difficult to be detected. A Nulling coronagraph, or nuller, can be used with a telescope to detect exoplanets by blocking out the on-axis glare from a star, improving the contrast of off-axis objects in the star's immediate environment. In the case of an interferometric nuller, the nulling mechanism is through total destructive interference. In a variation of achromatic interferometer coronagraph, MANIC incorporates a monolithic design, allowing it to have superior optical path length stability compared to a multi-element counterpart of the same design. The optical alignment quality is reproducible, given that the incoming beam is properly aligned to the input of MANIC. Also, since it has a fully symmetric design, MANIC has the theoretic potential to achieve perfect achromatic performance. The theoretic prediction of MANIC's nulling ability for a center wavelength of 648 nanometer is 10 to the negative 6 with 50% bandpass and 10 to the negative 7 with a 25% bandpass. To measure MANIC's ability to produce deep null, we design a system that uses deformable mirrors to correct for system-level wavefront errors. The wavefront sensor is focused to the deformable mirrors and therefore captures the pupil image. Wavefront corrections are generated after processing the pupil images with an image deconvolution technique. Due to pupil rotation, we can only null for half of the pupil. By scanning through half of the DM over a range of actuator values, starting from a flat mirror pattern, we produce the null image by assigning each actuator to their minimized value. The image deconvolution method can also be used to generate a maximized output. In order to perform contrast measurements, we need both the null output and the maximized output. Our contrast measurement is determined by taking the ratio between the brightest pixel in our null image and in our maximized image. The final contrast is found to be in the order of negative 1.8, which is not in agreement with theoretic predictions. We acknowledge that our system doesn't have the capacity to perform contrast measurement as it has a few limitations. For example, our deformable mirror is not at a pupil plane, and this may contribute to a certain amount of leakages in our null output. For future study, an upgrade is needed for the optical system. Having access to pupil planes at different locations will certainly aid to improving the nulling quality observed in the experiment.